Welcome to this explainer, where we are going to treat the Cambridge Mathematics examinations, specifically focusing on the highly demanding 0606 additional mathematics syllabus, but also pulling critical strategies relevant for 0580, 4024, 4037, and 4040. Literally like an archaeological dig. Think about it for a second. A top-tier Cambridge mathematics exam isn't just about blindly crunching numbers. It's a meticulous process. It's about uncovering the hidden clues buried deep within the question and layer by layer revealing the perfect, undeniably correct answer. Today we are zooming in on one of the most notoriously tricky areas of the entire syllabus, mastering the integration of trigonometric and exponential functions. I'm talking about integrating sine of ax plus b, cosine of ax plus b, secant squared of ax plus b, and of course, e to the power of ax plus b. To really understand the monumental challenge we are up against, I want you to visualize two very typical students taking this exact exam right now. Let's call them Alex and Sam. Alex is the kind of student who overloads absolutely every single answer with raw mathematical facts. Alex memorizes every formula in the textbook but provides zero structured analysis. We're talking about a student who just data dumps numbers onto the page, crossing their fingers and hoping the examiner magically finds the right ones hidden in the chaos. Then we have Sam. Sam rushes. Sam looks at a complex, multi-part integration question, completely skips over reading the critical command words like hence or show that, and sprints straight to a final numerical answer. No working out, just a sheer dash to the finish line. Both of these approaches are completely flawed and they leave massive amounts of marks on the table. In this explainer, we're going to look at their exact mistakes, understand exactly why the examiner's red pen comes out, and show you the proven, step-by-step strategies to transform those red marks into green check marks.
Let's start with an absolutely crucial number, 15%. What's really wild is that the integration of sine, cosine, secant squared, and the exponential function e routinely accounts for a massive 15% of the total marks in this specific additional mathematics exam. That is definitely not a minor topic you can just skim over. That 15% is literally the difference between passing and failing. It is the exact gap between a B and an A star. When Alex and Sam sit down for their exam, they look at that 15% weight and they completely panic. Alex tries to write down every single integration rule they've ever learned, entirely cluttering the page with irrelevant identities. Sam tries to do the mental math in their head, inevitably forgets to divide by the coefficient of x and drops the marks completely. But you are going to look at that exact same 15% and see guaranteed points. Why? Because by the end of this session, you are going to understand exactly what the examiner is secretly hunting for. You're going to know the structural secrets that turn a stressful exam paper into a predictable, highly scoreable puzzle.
To secure those high-value marks, we'll dive right into the examiner's actual playbook. We're going to cover 4 key areas today: the core theoretical principles you need, a highly structured 5-step methodology for tackling complex integrations, the critical examiner warnings that trap 90% of students, and finally, the ultimate method mark strategy to bulletproof your grade. All right, let's kick things off with Section 1, the core principles and decoding those tricky command requirements. When we talk about core principles in Cambridge mathematics, we are really talking about command word requirements. Command words are those vital verbs at the very start of the question, words like evaluate, deduce, or integrate with respect to x. Our rushing student Sam consistently loses marks because Sam actively ignores these words. If a question says hence, find the area under the curve, that word hence is not a suggestion. It is a strict, non-negotiable instruction. It literally means you must use the result you just proved in the previous part of the question. If you start from scratch, you get 0 marks. To effectively answer these, your mathematical architecture must rest entirely on what examiners call analytical depth. This requires you to clearly define your terms and show exactly how one mathematical step causes the next. This is where we introduce a game-changing framework. You usually hear about this in English essays, but it is incredibly powerful in advanced mathematics, the Peel framework. Point, evidence, explanation, link. Top students use a mathematical version of Peel to perfectly structure their answers. First, the point. Explicitly state the integration rule you are applying. For instance, clearly note that the integral of e to the power of ax plus b is 1 over a times e to the power of ax plus b. Second, the evidence. Substitute your specific exam question values into that framework. Third, the explanation. Show the step-by-step algebraic manipulation, ensuring your causal relationships are crystal clear. And finally, the link. State your final answer in the exact format requested by the question. Alex fails because Alex provides superficial breadth, just the point and the link, completely skipping the evidence and explanation.
Analytical depth means making your brain's entire processing pathway visible on the paper. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
And that beautifully illustrates our next core principle. Just look at this direct quote from the principal examiner reports. Top-performing students do not just memorize formulas in isolation. They actively connect these integration concepts to unfamiliar contexts across the entire syllabus. So what does a cross-topic connection actually look like in additional math? Imagine an exam question that asks you to find the exact area of a shaded region bounded by the curve y equals secant squared of 2x. Sounds standard, right? But to find the limits of your definite integral, you first have to solve a trigonometric equation where that curve intersects a straight line. Boom! That combines coordinate geometry, advanced trigonometry, and calculus all into one beautiful, absolutely terrifying question. If you only know how to integrate secant squared to get half tan 2x, but you absolutely cannot solve for those exact intersection points, your whole archaeological dig site collapses. You must be able to pull tools from completely different mathematical disciplines to solve the overarching problem. That is what Cambridge is testing.
Okay, let's transition to section 2. Here we're going to systematically break down the 5-step framework needed to confidently execute these complex transformations and actually get those green check marks.
To avoid Alex and Sam's mistakes, you must strictly follow this standardized sequence every single time you see an integration question. Step 1. Extract the relevant data. When you look at the function to be integrated, identify your a and b values immediately. Write them down. Step 2. Select the analytical framework. Ask yourself, is this a definite integral with given limits or an indefinite integral requiring a plus c? Step 3. Execute with clear notation. This is where you actually do the integration. If you are integrating cosine of 3x minus 1, your clear execution must physically show the 1/3 multiplier out front. Step 4. Verify your results. How do you do that? By quickly differentiating your answer to see if you get the original function back. The derivative of sine is cosine, so differentiating your results should perfectly map back to the exam question. It takes 10 seconds and it guarantees your answer is right. And step 5. Present using correct terminology. If the question commands an exact value, and you leave your answer as a messy, rounded decimal from your calculator, it will absolutely cost you the final accuracy mark. You must leave it in terms of pi, root 2, or e.
Within that exact 5-step framework, examiners are secretly testing your higher-order critical analysis skills. They want to see you question assumptions, evaluate the quality of your mathematical evidence, and justify your decisions. Applying higher-order analysis to integration really means recognizing when there are multiple ways to approach a problem and justifying the one you chose. For example, if you are integrating a highly complex trigonometric expression, can you use a double-angle identity to simplify it first? Does replacing cosine squared x with a half plus a half cosine 2x make the integration trivial? Evaluating these alternatives before you even put pen to paper prevents you from going down those horrible mathematical rabbit holes that just eat up your precious exam time.
When evaluating different mathematical approaches, it's not enough to just list facts on the page. You must actively draw evidence-based conclusions about their relative importance. Let's do a rapid-fire mental exercise together. Imagine a complex data scan challenge in front of you. You're looking at a chart of various definite integrals using sine and cosine over different boundaries. Your job as a top-tier mathematician isn't just to calculate them all individually like a robot, it's to extract the core mathematical trend. What happens when you integrate sine over a full period from 0 to 2 pi? The positive areas above the x-axis and the negative areas below the x-axis completely cancel out, giving you exactly 0. Understanding that comparative relationship mathematically saves you from doing tedious, error-prone calculations. You can look at the symmetry of the trig graph and instantly justify your conclusion using comparative analysis. That's how an A-star student thinks.
Moving into section 3, top examiner warnings and the interactive workshop phase. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @Ace the Exams IGCS and turn on all notifications so you never miss our weekly exam strategy sessions.
Okay, this table directly contrasts exactly where students lose points with what the examiners demand. But let's actually play a game here called Find the Flaw to really lock this in. Listen closely to this paragraph written by our rushing student Sam. Ready? Sam writes, to integrate e to the power of 4x plus 2, I keep the exponential the same, giving e to the power of 4x plus 2, and then I plug in my limits. Did you spot the major flaw? Look at the first row of our table, vague details versus precise mathematical terminology. Sam totally forgot to divide by the derivative of the inside function. Sam missed the 1/4 entirely. That's a classic error. Now look at the second row. Poor presentation of working versus strict conventions. Strict conventions mean aligning your equal signs vertically. It means clearly writing the integration symbol and the dx notation at the end. If you drop the dx, you are mathematically writing an incomplete sentence, and the examiner hates that. And finally, ignoring the specific scenario. If the question involves integrating a velocity function to find displacement, your answer needs to reflect that real-world context with proper units like meters, not just a floating, meaningless number.
Notice how the difference between a failing grade and top marks is simply the transition from throwing raw facts at the page to crafting structured, analytical responses. Let's do a mental speed writing challenge right now. I'm going to give you 30 seconds in your mind to rewrite Sam's flawed answer about integrating e to the power of 4x plus 2 perfectly. How would you phrase it using the PL framework? It should sound something exactly like this. Applying the standard rule for integrating exponential functions, I identify the coefficient of x as 4. Therefore, the integral is 1/4 multiplied by e to the power of 4x plus 2. Because this is an indefinite integral, I must also append the constant of integration, plus c. Wow! Do you hear the difference? That is a specific, highly structured response that an examiner can seamlessly award full marks to without a second thought.
Now we arrive at the most crucial part of this entire explainer, Section 4, the final system and the method mark strategy.
Listen, in the Cambridge grading system across 0606, 0580, and the others, you have accuracy marks for getting the final correct number. But far, far more important are the method marks, or M marks. The biggest glaring red flag in the examiner reports year after year is students completely missing out on marks simply because they failed to make their systematic processing visible. Remember our student Alex? Alex often does all the working out in their head, or scribbles it illegibly in the margins, and only writes the final answer on the main line. If that final answer is wrong, maybe they just missed a tiny negative sign when integrating cosine, they get 0 marks. 0! Because the examiner absolutely cannot see the methodology. You have to show them the map, not just the destination.
So, the absolutely crucial takeaway is this. The exam awards marks heavily for the process itself, meaning your clear notation and logical reasoning literally act as an insurance policy. Think about it. If a massive integration question is worth 5 marks, 3 or sometimes 4 of those marks might be method marks. If you show the correct substitution of your limits into your integrated function, but you completely mess up the final arithmetic subtraction in your calculator, you still walk away with 4 out of 5 marks. That's an 80% on a question where you got the final answer wrong. Method marks can and will save your overall grade, but they can only be awarded if your working is written clearly, step by step, right in front of the examiner's eyes.
To guarantee you capture every single one of these process marks, every layer of your mathematical dig must be meticulously documented. Whether you're doing 0580 extended or 4037 additional math, you need to follow these 3 fundamental rules to build your ultimate exam cheat sheet. Rule 1. Command word decoding. Explicitly deconstruct the question first so you know exactly what is being asked before you write a single number. Rule 2. Peel framework application. Format your working with clear headings, strict terminology, and highly visible causal steps. If you substitute a value, physically write substitute x equals 2 on the page. Show the linkage. Rule 3. The time management matrix. Don't spend 10 minutes sweating over a 2-mark question. Your clear annotation shouldn't mean writing a huge essay. It means writing crisp, logical, mathematical statements that respect the clock.
Ultimately, acing these Cambridge exams isn't just about integrating trigonometric or exponential functions correctly. It is about proving you have the professional discipline to evaluate evidence, avoid the exact pitfalls that trap rushing students like Sam, and explicitly lay out your logical path to the solution. So ask yourself right now, are you just trying to find a number, or are you revealing a masterpiece of mathematical logic? The real answer isn't just the final digit, it's the analytical trail you leave behind. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.